Good afternoon, everyone. My name is Brent Habersetzer, and on behalf of myself and my partner, Tucker Shannon, we are pleased to present to you the Grantham University Electronics Engineering Technology capstone project titled the Automated Grain Mill Kiosk. The purpose of this system is to take a manual hand crank grain mill, motorize it, and then automate the output so that an operator can enter a user-defined amount of grain that they would like to be milled. The system will monitor how much output that the grain mill has produced and automatically shut off when it has been completed. The first thing that I'll do is we'll step through and showcase some of the individual components and how we went about designing each facet of the system, and then I'll finish up with a demonstration of the entire system in fully functioning order. To provide a brief overview of the system, you can see that the entire system is encased in clear plexiglass to prevent operator pinch points from the devices when under motion. The overall dimensions of the system are approximately 22 inches cubed. At the center of the system, you'll find the manual hand crank grain mill, which has been converted into a motorized assembly. The 1075 RPM motor, 1/3 horsepower, provides the power to rotate the grain mill's flywheel. The first design challenge was to reduce the speed of that motor, as a high speed would wear out the grinding plates on the mill, causing overheating into the wheat. So a series of pulleys was used from 1.5 inches to a 4-inch, which is along the same shaft as a 2-inch up to the 12-inch flywheel. This effectively reduces the speed of the system from 1075 RPMs to 67 RPMs. This lower speed also results in a higher torque, which allows this relatively low horsepower motor to drive the overall system. The motor itself is actually variable speed and has 3 inputs that can be driven into low, medium, and high speed. The highest speed is 1/3 horsepower, the medium speed utilizes 1/6 horsepower, and the low speed utilizes 1/12. In order to overcome the initial moment of inertia of a system when it has not been rotating, the high speed is used. The motor is connected to a series of relays on the relay module, so when the system starts, high speed is enabled, 1/3 horsepower is made available to the system, and the flywheel begins to rotate, thus grinding the wheat. After approximately 1 second, sufficient energy has been stored into the flywheel to allow it to keep rotating. So the Arduino microcontroller then actuates the low speed relay, which converts that over to 1/12 horsepower. This results in a significant decrease in overall power consumption, as well as heat generation by the motor. The control system is driven by 5 volts, and you can see the 5-volt power supply here. And that's distributed out to the Arduino microcontroller, the relay module, and our instrumentation amplifier. The custom instrumentation amplifier circuit takes the output of a strain gauge and amplifies it approximately 1026 times so that it can be read appropriately by the Arduino microcontroller. On the custom circuit, we can see that there's a trimmer potentiometer, which allows us to adjust the gain resistor of the circuit to ensure that we're getting sufficient gain and to take advantage of the 1024-bit analog input of the Arduino microcontroller. The wires out from the instrumentation amplifier are connected to one of the major components of the system, which is the 1 kilogram strain gauge. This 1 kilogram strain gauge is configured in a wheatstone bridge configuration with resistors bonded to the side of the milled aluminum piece. As strain is applied to the leftmost side of the strain gauge, the resistors very slightly increase in resistance. With voltage applied to the wheatstone bridge configuration, that very slight increase in resistance results in a larger voltage drop, which is then amplified by our INA 333 instrumentation amplifier and then converted into weight in grams to measure how much weight is being sensed by our strain gauge. The system is controlled by a touchscreen HMI. The operator can select 120 grams, 240 grams, or 360 grams of wheat to produce. Upon pressing any of the buttons, we can see that it is updated into the current set point. And once the start button is pressed, the Arduino microcontroller will actuate the series of relays to enable the system to begin rotating and begin grinding the wheat. There's also a debug screen that is available to read and teach our ultrasonic distance sensor. The distance sensor located here monitors how much grain is being produced, and if too much grain is produced or there's a potential concern of spillage, as the level rises too high, the ultrasonic sensor will trip and it will deactivate the entire system to ensure no grain gets spilled or there is no overflow. Our pilot lights are indicating that the system is on, and our red light will enable when the machine begins grinding wheat. We also have a control panel that allows us to enable the system, and it is currently set into automatic mode. We can switch into manual mode to override the control system to just drive the motors individually and independently without any control system as a sort of backup. And now we'll go into the demonstration. Now, because grinding a cup of flour can take upwards of 20 minutes, I'm going to demonstrate the functionality of this system using whole unground wheat berries. You can see as an operator I can select 120 grams, 240 grams, or 360 grams, or 1 cup, 2 cups, or 3 cups of flour. The status indicates that we're updating the set point, and we can see that the set point value does update as we select it. In this case, I'm going to select 240 grams of flour or 2 cups of flour. I'll press start, and we can see that the current value is 22 grams. That's the weight of the container on the strain gauge at this time. As I slowly add unground wheat berries, we can see the weight increasing, but the mill will continue to run as long as that value remains less than the set point. As the mill produces more and more flour, the weight will go up, and eventually the system will turn on. Once the system has read 240 grams, the status indicator indicates that we are complete, and the red indicator has shut off, indicating that the system is no longer running. The last feature that I'd like to discuss is the ultrasonic distance sensor, which is being used as a level sensor to ensure that we don't have overflow or spillage while grinding grain. The ultrasonic distance sensor works by triggering an ultrasonic sound wave, which is then bounced off of the material down here and is received back by the sensor. The Arduino microcontroller is then programmed to measure the time that it took for that sound wave to bounce back and determine the distance away from the object to the sensor. We've already configured the sensor so that if anything breaks this top plane of this container, the entire system will shut off. So to demonstrate that, we're going to start the system. We've already got about 240 grams of wheat simulated have been ground, and the set point is 360 grams. To simulate a mound of flour that's beginning to pool up on one side, I'm going to use a piece of paper just to break the plane of the container. Once the sensor has identified that something has broken that plane, the entire system is immediately disabled to prevent the overflow or spillage. For the final demonstration, I'd like to showcase the entire system being used as it was originally designed. We add the wheat berries into the hopper. I'm going to select 120 grams and on behalf of myself and Tucker Shannon, thank you very much.